Everyone can still see my slides, correct?
Yes, correct.
Okay, great. All right, so we're going to cover a bunch of topics today. I'm going to be talking about radioactive decay, dose, exposure, and particle interactions with matter. So we're going to start off with pretty simple concepts here in radioactive decay. So, the basic idea that we're talking about with radioactive decay is we have a certain number of radioactive atoms that are in some form of unstable isotope. And how long does it take for these atoms to transform into a lower, more stable energy state or decay? And for any particular isotope, there's a characteristic mean time to decay, and the inverse of that is the decay constant. And nicely, this decay fits simple differential equation format, and this leads to what I'm sure everyone is familiar with from high school chemistry of straight exponential decay and half-lives of these radioactive materials. Now, keep in mind here, what we have in gamma here is the decay constant, not the half-life yet. And if we are talking about having a certain number of atoms decaying, these have that characteristic decay time, and you can calculate on average how many of those radioactive atoms are going to be left a given amount of time later. Now, when you get down to extremely low numbers of atoms, there is going to be some fluctuation here, but when we're talking about measurable radioactive events, the numbers are so huge that the variance in how many atoms are remaining after one half-life or 1 or 2 hours is essentially deterministic. Okay, so there's a couple factors that we can discuss here. The first is the decay factor. And this will be the fraction of radioactive atoms remaining after a certain time, t. And again, this is pretty trivial to calculate out. We simply have the starting amount, can multiply out by our decay factor, and analytically compute how much we're going to have left. Now, an important question when we're talking about SPECT or PET is how many gamma rays or how many emissions over that period of time are going to be associated with that amount of decay. So, in this toy example before, if we have 70.7% of our initial radioactive atoms remaining, then we've lost roughly 29%. And so out of that 10,000, we have 2,900 decays. Now, an important factor, which we'll talk about in following slides under decay schemes, is not every emission or not every radioactive decay is going to be identical, even for the same isotope. And each isotope will have its own decay tree, some of which, as these atoms are trying to find a more energetically stable configuration, they will undergo they can undergo a wide variety of different types of decay. And in the SPECT setting, that means that some of our decay events are going to lead to the production of gamma rays, some are not. And so if, in this toy example, we have 89% of our decays leading to emission, and the other 11% are through internal conversion, some other form, we're going to end up having 2,600 gamma rays emitted. Now, this is important when we're trying to think about counting statistics, which Lisa's going to start talking about next week, in terms of how much activity, how many radioactive atoms do we need to inject a patient with to get a certain number of counts out on the far end. And partially that's going to be due to the rate of decay of the radioactive nuclide that we inject a patient with, how quickly it decays, how many gammas per second we get, or how many decays per second we get, excuse me, and then based on the decay tree of that particular isotope, how many gamma rays are we going to get out? Okay, so a much more familiar metric that goes back to high school chemistry is the half-life. So the half-life is the average time until half of the radioactive atoms remain. And if you just plug in the decay factor, it becomes, you can, up here, so we've got our number of radioactive atoms at time 0, and we want to solve for at what time is our half of our atoms remaining, or half of them remain radioactive. We can solve this out pretty simply, and it will have log 2 divided by gamma here, and so we can end up having a much more intuitive rate of decay of the half-life. And so for a standard spec tracer, or well, many spec tracers use the radionuclide technetium-99, and this has a half-life of 6 hours. So in terms of nuclear medicine, this is one of the more long-lived isotopes. You know, usually when you think about radioactive isotopes and things that are long-lived, in popular imagination, we have things coming from, say, Chernobyl or nuclear disasters where you have, you know, half-lives on the order of years, or, you know, for extraordinarily long-lived isotopes, you know, decades. But when it comes to medical imaging, 6 hours is on the half-life, or on the long side of half-lives, excuse me. And so, you know, on the shorter end, the things that we'll see commonly are carbon-11 with 20 minutes, or F-18. It's in the mid-range with about 2 hours. And on the very long end, the longest end we will generally see in nuclear medicine are radiometals, things like zirconium-89, which have a half-time of about 3 days. But, you know, just as a sense of scale about how quickly these things will decay on the medical imaging side. Okay, so usually when we are calculating out the decay equation of how long it's going to take something to decay, we're going to be talking about half-time. So this is the equation we will use here. We've got the number of radioactive atoms at time 0 with this exponential decay of the negative ln2 times the time that's passed divided by the half-time. This is pretty simple because once the time here reaches the half-time, this collapses to 1. This is e to the negative log 2, so that's 1/2, and that will collapse down n equal to be 1/2 of n0. So we can calculate this out from the previous example in the exact same way, just plugging in something different than the decay factor with the more intuitive half-life. Okay, so as I was mentioning, here's a range of radioactive isotopes that will come around. Not shown on here are the really short ones like carbon-11 with 20 minutes, or oxygen 018 with his around 2 minutes, you know, extraordinarily short-lived radionuclides for the use of medical imaging. Okay, so when we talk about activity, so far I've only talked about straight number of radioactive atoms, but when we're talking about radioactivity, a quantity of radioactive material, we're talking about the activity of it. And when we talk about activity, it's the change in radioactive units, radioactive atoms per unit time, which is essentially the decay rate in decays per second. So this is going to be expressed in curies, most commonly in America, or if you're following SI units, it's going to be in becquerel. And 1 curie is 3.7 times 10 to the 10th disintegrations per second, and 1 becquerel is just 1 decay per second. So a millicurie is the same as 37 megabecquerels is the simple conversion there. And it's easier to remember that, so not much more nice round numbers than 1 megabecquerel equal 27.03 microcuries. Okay, so typical quantities used in nuclear medicine are less than 30 millicuries. 30 millicuries is on the really high end. You know, a standard FDG in the clinic now is closer to 10 millicuries. All right, so the same decay equations work for activity as work for the total number of atoms. We can use the half-life just the same amount. So if we have 10 millicuries of Tech-99 at 8 a.m., we'll end up having 7.07 millicuries. Now, keep the important distinction to remember when thinking about number of atoms versus activity here is the 10 millicuries is telling us how many, what's the decay of this radionuclide over time. And if you could convert back to number of atoms, going back from the absolute rate of decay and using, calculating out the actual molar number, the absolute number of atoms we have of Tech-99 if there's 10 millicuries of it. But when we're talking about these things in the clinic, far more importantly, we're going to be thinking about 10 millicuries or things on the activity basis, not the molar amount level purely of the radioactivity. And that goes back to what George mentioned on Tuesday about the tracer principle. In nuclear medicine, we are administering patients with such tiny amounts of these molecules that your body treats one of them the same way it would treat a non-radioactive, naturally occurring version of this. And so what we're interested in is, what we can see, and that comes from the activity here. Okay, so, how much activity is in 10 to the 10th atoms of technetium or I-123? So the activity is the decay rate times the total number of atoms, right? So you can, if you know this decay factor for your given radioisotope, you can just do a pretty simple algebra calculation to figure out what the activity level here is. And so given equal number of atoms, we have about twice the activity in the Tech-99 as we do in the I-123, and that's because the decay factor is about twice as fast for Tech-99 as it is for I-123. So they're decaying twice as fast, thus we have twice as much activity. All right, so there's a couple methods for determining decay factors. We can calculate them directly. You can just look up tables. Now, for standard practice, just looking things up in a table works pretty well. These things have been mapped out. If you know what the isotope you are dealing with is, or you can just estimate them. Now, the table of decay factors can be helpful if, say, there's been a spill in your lab and somebody's broken the rules and hasn't documented that they spilled some activity. And if you come over with a radiation detector, you can see that something is spilled on the floor, but you don't know what it is. Now, maybe it's carbon-11, and if you wait 5 hours, it'll be gone completely. Maybe it's zirconium-89, and you need to wait a month before it's gone completely. So it's important to know what those are. So you could measure decay over time, and then do a backwards lookup and say, okay, well, what isotopes are decaying this slowly? And you could figure out, who is it that's working with copper-64? Who broke the rule in the, who spilled and didn't document it? Who here is working with copper-64? Okay, so determining the activity that you have, let's say we've got a vial that has 10 millicuries per mil of F18 at 6 a.m. And if we want to figure out, in the clinic, they want to inject 1.5 millicuries at 9 a.m., how much should I take out of my stock vial for this patient? Well, you can do those calculations pretty simply and say, what's the activity per mil going to be in 3 hours from now? So we've got 180 minutes divided by the half time of F18, 109.8 minutes, times log 2, negative log 2. And that means that at 9 a.m., our stock will be 3.2 millicuries per mil. And then you can say, okay, well, that means that I need to take out 0.47 mils for my dose at that time. All right. So if you're looking up tables of decay factors, one limit to this is they cover pretty limited periods of time. Usually in, well, it'll depend on the isotope, but something like, in increments of 15 minutes or, every hour. And you'll just have to, estimate out intermediate factors if you don't have the full, if you haven't calculated these things out fully. Now, the calculations for doing decay factors are pretty simple, so you don't need, if you want to know something exactly, it's pretty easy to just punch it into those equations and calculate it out yourself. But if you want to look at a table of decay factors, you could look at something like this. So this is a table for Tech 99, and you would just go, say how much activity is going to be left in 4.5 hours. Okay, 59.5% will be left in 4.5 hours. And so that'll be a good rule of thumb if you're trying to figure out generally how much activity you're going to need to make for the day if you're working in the radiopharmacy. But if you're working on your own experiments, it's usually best to just punch these things into the actual equation and figure it out yourself. Okay. The other thing you can look at is these universal decay tables. So by those decay equations that we looked at, you can always normalize everything into number of half-lives because half-life is when half your activity is going to be gone. So you can just fit these things in here, and if you know roughly your half-life, you can say, well, when am I going to have 20% of this left? You can just look over here and say, okay, well, we're a little over 2 half-lives out. We'll have that amount left. I know my half-life for this particular isotope is 2 hours, so I've got to wait 4.5 hours roughly. So these things help for good rules of thumb, but again, being exact is usually more important, and these aren't hard equations to solve. Okay. So I'm going to skip through a couple of these things to get into some ideas of multiple decay schemes, which complicates things a little bit. So here we're going to be talking about not something quite as simple as our common decay schemes, in which we've got a radioactive parent atom that decays into a stable radioactive daughter. Instead, here what we're talking about is a radioactive parent isotope that decays into a radioactive daughter isotope, which then decays into something stable. So we've got 2 separate decay constants here, lambda P, lambda D. All right, so how do we figure out the activity and amount of daughter atoms that we have over time? Well, we know what the decay equations are for the parent, right? So we can multiply, we can just create some simple ordinary differential equations that will help us calculate out what the number of daughter atoms is going to be and what the activity there is. Okay. Now, these are not things you're going to need to memorize, but what the important factor is to look at here is, where are we going to reach equilibriums with these things? Okay, so let's look at long times, and we can say, what is when the activity in daughter over the activity in the parent is constant, and we reach out in equilibrium. So we're interested in, if we start with only the mother radionuclide, how long does it take for things to stabilize and we've got a constant ratio between the two? Because the numbers aren't going to be constant, right? This isn't simple growth curves. These are constantly decaying, so we can only talk about their ratios being constant. Right, so the first one is when we have secular equilibrium, and this is when decay time to the parent is much, much higher than that of the daughter. All right, so this means that the parent is decaying much slower than the daughter, right? And what this means is you start with all parent and no daughter, and over time, the daughter activity is going to rise asymptotically to the amount of the parent. But now the activity here, remember, is we're measuring disintegrations per second. This isn't in number of atoms, right? And so eventually, if the decay time of the parent is much, much slower than that of the daughter, eventually the equilibrium you're going to reach is when, for every decay we get of the parent, that then converts into something of the daughter, and that's going to equilibrate with the daughter decaying as well. And so those activities will reach each other. Notice here, the parent is decaying so slowly, this basically looks like a flat line. Now, the rate at which we're going to reach secular equilibrium is going to be dependent on this equation here. And so you can calculate this out by the number of half-lives, how close we're going to get up to that true ratio of equality there. Okay, now something that's going to come up slightly more often is transient equilibrium. And here, again, we look at where the parent time is larger than daughter time, but not to the same extent that it was for secular equilibrium, right? Now, in transient equilibrium, you'll rapidly have rise up to the parent activity, and these will then decay down together. Now, this ends up being important in the production of several isotopes, most notably in technetium-99. Okay, so technetium-99 is one of the most common radioisotopes used in SPECT imaging, and the way that you produce Tech-99, you don't need a cyclotron or anything like that. You have a molybdenum generator, and so you've got this generator that is basically just a big cylinder with molybdenum-99 in it, and it will decay into technetium-99 over time. And what you do is you basically wait for this generator to reach transient equilibrium, and that means that the activity of your parent and daughter are equal, and then you will flush your generator with a solution in which the technetium is soluble, but the parent is not. And so you'll get this flush of technetium, and then in the idealized sense, your generator has no more daughter in it, and it will start generating that again. So here's a cartoon example of this, where the dotted line here is the activity of the parent, and these solid lines are activity of the daughter Tech-99. So it rises quickly, and we flush it out to make our technetium-99 doses for the day. And you wouldn't want to let it go longer than 24 hours, because if you go longer than 24 hours, you're not actually gaining anything, because you've already reached this maximal point, and it would just decay away inside the generator. And so the Tech-99 generator works out quite nicely because we reach this transient equilibrium at about 24 hours, which means that the radiopharmacy can just do an elution the same time every day and essentially get their maximal amount out. Now, you can do multiple elutions in one day and not get the full amount of activity that you want, but you can get partial activity out multiple times a day here. Okay, so that's basic of decay. And now before I go on to talking about how the products of that decay interact with matter, do we have any questions here? Okay, if that's the case. All right, so, whoops, am I not sharing the screen? Okay, are you able to see this slideshow here?
Yes.
Yep.
Okay, all right. So in that first set, we were just talking about the rate at which these guys decay and how to measure that out. Now, in nuclear medicine, we're really interested in not, the primary interest here is the products of those radioactive decays. So I'm going to be talking about three broad methods of interaction here. How electrons and positrons interact with matter, how photons interact with matter, and how proton and alpha particles interact with matter. Okay, so first up, electron and positron, beta minus, beta plus. These have mass of 511 MeV or 511 or 0.511 MeV, 511 keV, and these are important in PET imaging on the positron. The P in PET is positron, and in radiation therapy. Now, photons have a wide range of applicability. George mentioned that. He showed the photon spectrum in that lecture on Tuesday. There's optical imaging, X-ray, CT, SPECT, and PET are all photon or gamma/X-ray imaging modalities. Protons are quite important in imaging as well. These guys are real massive. This is what we're measuring in MRI, and there's also proton therapy for cancer ablation in radiation therapy. And lastly, and the biggest particles here are the alpha particles, and these are used in radiation therapy as well. Okay, so let's start talking about electron and positron interactions. And the two broad areas we're going to talk about here are Bremsstrahlung and electron-positron annihilation. So in Bremsstrahlung, did anybody take German at any point and can translate Bremsstrahlung?
I'm from Germany. So it's breaking radiation.
Yes, it's breaking radiation. Breaking as in slowing, not as in destroying. So if we've got deceleration or deflection of a charged particle, that means it's losing some of its kinetic energy. But we're not allowed to break the laws of physics. That energy just doesn't disappear. It can be converted into photons. Now, this is not a discrete event. These can be decelerated or deflected in a large variety of ways. So this will produce a continuous spectrum of emitted energies. From a small photon production, if it's deflected slightly, or a large energy photon if it's completely stopped. Okay, and this is useful in CT imaging because this is how we're producing our X-rays by shooting an electron beam at a dense deflector, most commonly tungsten, and this will create an X-ray production. And these X-ray beams can then be used for CT image acquisition. This is also problematic for the storage of some beta emitters because while you may be able to block a decent amount of these betas, if you shield them improperly, you can end up producing a lot of Bremsstrahlung and then producing extra X-rays and need to stop those as well. So it can be helpful and problematic. Now, if we look at what that spectrum that I was talking about of Bremsstrahlung might be, the relative intensity of the X-ray energies that are produced. We've got this maximal energy, and that's if the complete conversion of that energy goes into creating a new photon, but that's relatively unlikely. More commonly, we're going to get lower energy gammas or X-rays produced out of this. Okay. Now on the positron side, so positrons are the antimatter particle to an electron. They are identical except they carry positive charge. Okay, and this is what we're primarily imaging when we're looking at PET imaging, positron emission tomography. Okay, so we've got our unstable radioactive atom that is going to decay and produce a positron and shoot out a neutrino to keep things balanced. But when it shoots out that positron as part of its decay, that does not have zero kinetic energy. So it can't immediately interact with an electron. So it's going to bounce around inside the test tube, inside the patient, inside the injection syringe, whatever, until it loses enough kinetic energy to actually end up interacting with an electron. Now, the range that this travels in the body is not always going to be insignificant. And the higher the energy of that positron, the longer it's going to take for it to decay, for it to lose that energy and then interact with an electron and produce the gammas we're looking at. So, in PET, preferentially, all else being equal, a very low energy positron emission would be good for imaging, because what we are detecting and where the decay actually happened, which is what we want to detect, would be very, very short. A high energy would be bad for image resolution, because essentially you'd have this big Gaussian blurring of the random walk that your positron takes before it interacts and you can detect it. Okay, so when they annihilate, when the positron and the electron meet, they annihilate and produce two high energy gammas that fly apart at 180 degrees. Okay, so a couple points here. Why are these two gammas 511 keV in energy?
The rest mass of the electron, correct?
Yeah. So these guys are converting completely energy. So those are the rest masses. Again, we got to obey the laws of physics. We can't create things out of nothing. Okay, next point. Why are they flying apart at 180 degrees? Okay, again, this is just simply obeying laws of physics, right? We have to preserve momentum. So we can't have them fly out at 90 degrees from each other, because there's a net momentum there. And then the last point is, I lied when I said they flew apart at 180 degrees. This is plus or minus half a degree here. And so where's this coming from if we have to preserve momentum and obey the laws of physics? Well, I said that positron has to lose enough kinetic energy so that it can interact with an electron, but it doesn't have to lose all its kinetic energy. And any electron it's going to meet with is certainly going to have some kinetic energy. So there's going to be some set net momentum in that pair before they are at the point of annihilation, and that has to be maintained in here as well. Okay, and when we talk about PET imaging, we're going to be talking about how this 0.5 degrees can actually have a significant effect on image resolution. Okay, all right. So let's talk about photon interactions. Excuse me. So this is where the majority of this segment is going to be on. So there are four main areas that we can have this effect. The first is the photoelectric effect. The second is Compton scattering, then coherent scattering, and pair production. All right. Now, before we talk about those specific effects, we're going to be talking, let me talk briefly about attenuation. So attenuation is anything that is going to prevent a beam of photons from reaching a target. You know, some width x of an absorber is going to stop some amount of a photon beam from reaching the detector, right? So there's something happening inside this absorber that's preventing them from getting over to the detector here. And luckily, things are quite simple. And if we have a uniform absorber here, this can also be described by simple ODEs, which lead to a simple exponential loss of incident photon energy. Okay, and this is based on both the thickness of the material and specific properties of the material we're going through, the linear attenuation coefficient. And this is in inverse length, right? Because this exponential has to end up being unitless. X is in a unit of length, so this has to be inverse length. All right. So just based on this, how wide of an absorber would you need to completely stop an incident photon beam? It would have to be infinitely thick, right? To get this to zero, the only way that works is if X here is infinity. So it doesn't matter what material you have. It doesn't matter if it's a feather, you know, a feather pillow or a stack of lead. You would need an infinite thickness to completely stop an incident photon beam. Yeah. But anything that's preventing it getting to the other side here is attenuation. So let's look at, you know, what it is that's happening inside this absorber that's leading to this attenuation. Okay, so the first element is the photoelectric effect. And so the general idea here is we've got an incident photon, and it's going to interact with the electron shell. It will transfer that energy to an ejected photoelectron with some given energy here, where this is our incident energy of the photon. This is the binding energy of that electron. Okay. Now, if we remember from physics and chemistry, the inner shells are more stable and they have a higher binding energy. Electrons are much more happy to be in those inner shells than in the higher shells. So it's harder, well, it requires more energy to eject a inner shell electron. But if you have enough energy, so if this incident photon has more energy than the binding energy of any of the shells in this particular atom, the ejection from the inner shells is more likely. Now, this can seem a little counterintuitive, but does anybody have an idea why you are more likely to eject one of those inner shell electrons rather than one of the weakly bound outer shell electrons? Think about how much empty space there actually is in the electron cloud, right? So, you know, in those outer shells, there's the electrons that are there are not nearly as dense. So when we're talking about the probability of an electron being ejected, you know, before we even have the chance to eject it, you know, see if we have enough energy to kick that electron out, it first has to interact with that electron. And electrons in those inner shells are much more dense. So you are much more likely to interact with an inner shell electron in any case than you would be with an outer shell electron. And if you've got enough energy to kick it out, it's going to happen. So those inner shell electron ejections are much more likely to happen if you have the energy to do it. The probability of this occurring goes up with the Z of a material. So the big, heavy, dense materials, you're more likely to have that photoelectric effect, but it goes down with the energy to a cubed factor of the energy. So as you get to really high incident photon energies, the probability of any kind of photoelectric effect goes way down. But if you are going to have one, it's going to be in those inner shell electrons. Okay, now in photoelectric effect, all of the photon energy is transferred to the electron, leading to the ejection of a photoelectron and the production of either characteristic X-rays or Auger electrons. So what happens to begin with is we've got this incident photon. It interacts in this inner shell, transfers all its energy, and kicks out one of our electrons. But we now have an empty space in one of those highly desirable inner shells. And that makes this a very unstable, very energetically unstable configuration. And so the electrons here want to rearrange themselves and fall into these lower orbits. And so what we can have is we can have an electron from a higher shell fall into a lower shell position. But again, right, so this is becoming energetically more stable, but we have to obey the laws of physics. That energy has to go somewhere. And in this case, it's in X-ray production. And X-rays are a specific type of photon that originate out of the electron shell. So these here, we've got an X-ray falling from 2s down to 1s, and the energy of this X-ray is going to equal the difference in binding energies between these shells. And so that's why this is a characteristic X-ray. When we produce X-rays in this fashion, they are going to be monoenergetic, simply the difference between these shells. And that's a way that we can measure what the difference in these binding energies actually is by the production of measuring the energy of the X-rays produced in this fashion. The other option is, instead of this energy being transferred into photon production, creating an X-ray, instead it can be transferred to another electron in the outer shell, kicking it out, making Auger electron production. So we get a second electron knocked out of here, but no photon production. All right, so what happens if, instead of transferring all the energy of the photon to an electron, we only transfer some of it? All right, this is what's called Compton scattering. So again, we've got an incident photon. It interacts with the electron cloud, and it scatters by some degree theta. And it doesn't lose all its energy, it only loses some of it. So it's got this scattered energy here, and we can have an ejected Compton recoil electron. Now, this is much more common with outer shell electrons, because since they require much less energy to interact with, it's more likely that it's going to interact and not lose all of its energy. And when this photon is scattered, it's scattered with a reduced energy and a direction. And so this is pretty problematic. This is going to be one of the most common things we need to correct for when it comes to CT, PET, or SPECT, because in all those cases, we're measuring the flux of photons through the body, and as they get scattered, that's going to make it more difficult for us to know where they actually ended up with. So, imagine we're trying to measure this photon as it's coming through. We expect it to show up somewhere over here, but it's actually going to show up on a detector somewhere up here, right? And so that's going to lead to decreased image quality and reduced image resolution. And again, when we get to PET and SPECT modules, we'll talk a bit more about how this is directly leading to image quality reduction and how we can hopefully correct for it. All right. Now, the energy of our scattered photon is directly and solely related to the scattering angle that we have here. Okay, it's pretty simply calculated. Now, so if this doesn't scatter at all, and our scattering angle is 0, right? This is going to equal 1. This quantity goes to 0. This quantity goes to 0, and we just have E naught over 1. So our scattered energy is equal to our incident energy. Now, what angle would equal the maximum amount of energy loss? So what angle would end up with the smallest E scatter?
90 degree.
Well, 90 will give you a lot of it, right? Because 90 will be, this will go to 0, and you'll have E naught over 1 plus E naught over MC squared. But if you scatter completely reverse direction and have a 180 degree scatter, right? Cosine of 180 will be -1. So we'll have E naught over 1 plus 2 times E naught over MC squared. Now, complete reversal scattering is extremely uncommon. You are much more likely to scatter in a forward direction than you are fully reversed. And the exact probability of each scattering angle is related to the incident photon energy. So if you come in with a lot of energy, you're much more likely to scatter with a low angle than you are if you come in with a low photon energy. Very low photon energies coming in are much more likely to have scattering in all directions. But it's not a uniform random scattering here. It is related to the incident energy. All right. The next we're going to talk about is, photoelectric is completely losing energy, transferring everything to electron cloud. Compton is transferring some, and then in coherent scattering, the photon is deflected with essentially no loss in energy, and it just interacts with the atom as a whole. Now, this is only really important at very low energies of photons, below 50 keV, so it's very uncommon to come up in medical physics applications. However, it's extremely common in everyday. This is the reason the sky is blue. So if you have annoying young nieces or nephews or children of your own that are pestering with questions about why is the sky blue, you can tell them it's because of Rayleigh scattering. This is because the blue wavelength lights are more likely to undergo the Rayleigh scattering in the atmosphere, so we preferentially get scattered blue light, hence blue skies. All right, so lastly here in photon interaction, we're going to talk about pair production. Now, this is when an incident photon has so much energy that it's going to pass through the electron cloud and interact with the nucleus itself, and produce an electron and a positron with nuclear interaction here. Now, the incident photon energy here has to be above 1.022 MeV. That's because we need enough energy to create the rest masses of both an electron and a positron. Now note here that these guys are not going apart at 180 because they need to preserve momentum. So it's based on the incident photon direction where these electron positrons are going to be produced. Okay, so that linear attenuation coefficient that I mentioned before is a combination of all those factors. Any of those possible interactions can happen in that absorber material, and any that do occur are going to prevent it from reaching the detector. So attenuation is not just being absorbed in this material. It can be things that are scattered out and just don't hit our detector anymore. It's the combination of all those factors. So let's look at the combination of those factors for two different absorbers. So on the left here, we've got the interaction spectrum for water, and on the right, it's sodium iodide, a photodetector in SPECT and PET. So on the x-axis, so the amount of interaction we're going to have is a function of that incident photon energy, right? So on the dotted line here, which effect is this? One that's rapidly decreasing as energy of the photons increases. That's the photoelectric effect, right? So as the photoelectric effect decreases to the third power of the energy, right? So this is decreasing rapidly. What's this level of interaction here that starts at high energies?
Pair production.
Yes, okay. And then this red dotted line here is the one that's remaining. This is our Compton scattering. Now you can see at low energy, and the solid orange here is the sum of all of them. Okay, so you can see at low energies, it's completely dominated by photoelectric. But when we get into the 100 keV to 1 MeV range, it's almost entirely determined by Compton scattering. So in the body, which other than bone, we can mostly treat as water for these attenuation purposes, it's almost entirely based on Compton scattering for the gammas we look at in SPECT and PET. Okay, now if we look at a denser material, sodium iodide, this has a radically different interaction spectrum than we saw in water. So we see this similar Compton effect here, right? And again, we see pair production starting at high energies only, but we see this strange discontinuity in the photoelectric effect, okay? So what's going on at this discontinuity here? And I'll give you a clue that the K here is important for what's happening.
Like the energy levels?
Yeah, so this is the energy of the K electron shell, right? So the two things we know about the photoelectric effect is in a given material, the probability of its occurrence is going to go down with the third power of its energy, right? So that's what we're seeing happening here, okay? But once we get here and suddenly reach the binding energy in our K shell, a second thing we know about the photoelectric effect comes in with importance, and that's that we are preferentially going to eject things from the K shell if we have enough energy to do it. So as soon as we have enough energy to do it, suddenly there's a whole new type of attenuation that can happen. Suddenly we're allowed to have photoelectric effect interaction with K shell electrons too. And so that's why we have this new spike that happens, right? But then as the energy increases here, we're less and less likely to have any type of photoelectric effect with the inverse third power of our photon energy, as that decreases along. Okay, so to give you a rough idea of what these linear attenuation coefficients might be, this is a table of the most common materials that these gammas are going to interact with in the nuclear medicine setting, and two common energies. So 140 keV, this is in the range that we're generally going to see gammas in SPECT, or 511, which is the photons we're seeing in PET, right? So this 511 is that mutual annihilation of the positron and electron, and we create two 511 keV photons. So lung, which is mostly air, is really bad at stopping both types of these guys. water, general soft tissue is roughly equal. We have about a 50% increase. It's 50% better at stopping these lower energy spects. Similarly with bone, it's about twice as good. But then when we get into things like sodium iodide and LSO, where a lot of photoelectric effect can happen, where photoelectric is much more likely to happen at these low energies, right? So that can happen a whole bunch more at these low energy gammas than at the high energy gammas. So sodium iodide and LSO, these are two different detector materials used in either SPECT or PET. And you can see that they're very, very good at stopping SPECT per centimeter, and they are much better than, say, bone or soft tissue is at stopping these 511 keV photons, but they're much better at stopping those low energy guys. All right, so let's take a cartoon example in a patient. So let's say we've got some kind of cardiac tracer in SPECT, and we've got indium-111, a common SPECT radionuclide. Okay, so we've got 140 keV gamma that's emitted from this, and it interacts with the bone of this patient and then gets scattered. All right, so the energy of this scattered photon is going to be completely defined by that theta. Okay, and from SPECT, this is problematic because instead of measuring something coming along this line of response here, if we detect this guy, we're going to think activity originated somewhere along here. So we'd falsely place this signal in probably liver activity as opposed to the cardiac activity we think it actually is going to be. Okay. Now, in the PET side, again, we've got, here we've got F18, and instead of having one photon emitted, we're emitting two at 180. Now, to detect the signal in PET, we need to simultaneously detect both of these guys. So the probability that we measure this signal, right, is the probability that we measure that this photon does not get attenuated times the probability that this photon does not get attenuated. But this leads to a really nice feature that makes attenuation correction in PET somewhat simple. Because if we look back at probability of attenuation, right, it's our incident beam, or the beam intensity at distance x is the beam intensity at origin times this exponential, right? And so if we think about this as a single photon instead of attenuation, this is just probability of it escaping the body, right? Now this is for a uniform material with a uniform mu. However, if we're looking at going across a whole bunch of different tissues, instead we can think of e to the minus line integral of mu's all along here, right? So we have an infinitesimally small distance times our mu for that distance, and we can just do the line integral across all of that, right? But the probability that it's going to escape both sides is the product of those two, right? So we've got e to the line integral of the right side here times e to the line integral on the left side. So as we multiply those exponentials, we sum what's up here. So we sum those two line integrals. And so the probability of detecting it is going to just be, or the probability of attenuation is just the line integral of all attenuation along this line of response, which means that it doesn't matter where this annihilation event happened across this line, the probability of it escaping and being detected is the same regardless, which makes attenuation correction somewhat simpler on the PET side. Okay, so a couple last little points about attenuation. Similarly to a half-life in radioactive decay, we can talk about half-value thicknesses, and that's simply how thick a given material has to be to stop half the incident beam, right? So you can pretty simply plug that into our attenuation equation here and find that it's ln2 over a linear attenuation coefficient. And related to that is the mean free path, which is the expected distance one of these photons is going to pass without having any kind of interaction, which is inversely related with our linear attenuation coefficient, and you can also relate that to the half-value thickness as well if you'd like. Okay, so lastly, in this section, I'm going to be talking about proton and alpha interactions. So protons and alphas are extremely heavy particles in comparison to what we've been talking about before. So for a given energy, they're traveling much slower than, say, a beta particle is, right? Because energy is going to be mass and speed, okay? So for a given energy, are these guys going to have a higher or lower probability of interaction per unit distance than photons or electrons? Well, they're traveling much slower through tissue, so they end up having a much higher probability of interaction with tissues than photons or beta particles are. So alphas are very scary if they get inside you. They can do a whole bunch of damage to soft tissue, but the clothing you're wearing is sufficient to shield yourself from alpha radiation if it's outside the body. So you don't need to worry too much about those. However, if they get inside the body, they can do a whole bunch of damage, which actually makes alpha emitters a really common candidate for targeted radiation therapy. So analogous to PET, right, we create a radioactive molecule that will target cancer cells so we can see the cancer in the body. Okay, well, if we have the exact same tracer, but instead of having it attached with a radionuclide that gives us a positron that we can then measure through its resultant gammas, if it carries a radionuclide that decays by alpha emission, we can suddenly get those really damaging short-range alpha particles being emitted right next to the tumor where these tracers accumulate, right? So not only are they doing a ton of damage, they don't travel a long distance, so you don't have to worry about them, spilling out into nearby healthy tissues, and they can do a bunch of damage and help kill the cancer. So the alphas can be helpful there, but they're not going to travel a very long distance. All right. So these heavy particles like protons go through what we'll describe as specific ionization, and that's the number of ion pairs produced per unit length that travels. Now, one of the really nice traits about protons is that this is not a linear constant, and it doesn't decay as it goes through tissue. In fact, it increases up to what we call the Bragg ionization peak. So as it's traveling through tissue, it's going to be producing some level of ionizations, doing some amount of possible damage to the tissues it's traveling through. But as it slows down through tissue, the specific ionizations are going to increase as it reaches the end of its path and deposit almost all of its energy in a pretty narrow window near the end of its path. And what's nice about this is we can do radiation therapy planning with protons for proton therapy, where if you know exactly where the tumor is from prior imaging, you can set up multiple treatment paths of your proton therapy gun so that your tumor lands right in here. So a huge amount of the vast majority of the energy is deposited right where you want it to, damaging the tumor and not doing a lot of damage to healthy tissues that it has to pass through on the way to the tumor. Okay, so I've got a bit more time here where we're going to talk about dosimetry and exposure to radioactivity. So once these these radionuclides, their activity decays in the body, they produce photons or photons, beta particles, maybe alpha particles in the body. How do we measure what effect that has on a patient or a subject or somebody walking by the cyclotron that's not properly shielded by accident? Okay, so before we talk about that, are there any questions in the particle interaction section? All right. All right, so the last thing we're going to talk about here is exposure and dose. So what are we talking about when we talk about exposure? Well, we're talking about the amount of ionizations that are produced in a given volume of air by that radiation. So the way we'll measure this, you can standardly measure this, is by using an ionization chamber. So you can have a sealed chamber just filled with gas with a positively charged plate and a negatively charged plate. And as your ionizing radiation passes through here, it's going to produce ionizations. And as those guys ionize, they're going to travel to their respectively charged plates, and then you can measure current traveling through this system, and that current is going to be directly related to the number of ionizations that are occurring, and you can measure quantitatively the number of ionizations that occur. Now, note that in this case, we're using air as a reference material for the amount of ionizations that occur, analogous to the way mercury is used to measure air temperature. Okay, so now the signal that we're going to get out of this machine, for the amount of electrical current running through it, is going to be dependent not only on the amount of radiation that's traveling through, but also on the voltage that's set up here, right? So let's say we've set a really weak voltage difference between our negative and positive ends of these plates, okay? That means that any ionizations we produce are going to travel to these plates pretty slowly, and on their way to the plate, they have a chance to recombine and lose their net charge and no longer travel to the plate. So that happens here, where this is the recombination zone, where not everything that gets ionized is going to reach one of those plates and produce a current. If we reach a range here where we've set up significant voltage significant enough that all our ionization events are going to reach the plates, well, what this means is that we can count individual, count the current going through there as analogous to the number of ionization events that happen, right? Because if every ionization event reaches the plate, then the current there is going to be directly proportional to the number of ionization events. Okay. Now, if we jack that current up a little bit higher, then not only is every one of these ions going to reach one of these plates, but they are going to be accelerating pretty rapidly on their way to these plates. And as they're accelerating along the way, they can slam into non-ionized molecules in there, splitting them apart and creating secondary ionizations that will travel to these edges here, okay? So as you ramp that up, more and more of those secondary ionizations is going to occur up to this region here, in which a single ionization event has enough, will then avalanche into ionizing the entire chamber, okay? And so what that can let you do is every time you get current through your system, that's a full ionization of your chamber, all right? And typically we're going to be measuring things either here in this current mode or out here in region 4 with our survey and dose meters. All right, so what is our units of exposure? So our units of exposure here are Röntgens, and it's defined as the amount of X-ray or gamma radiation that will lead to 1 electrostatic unit of charge in 1 cubic centimeter of air at standard temperature and pressure. Okay. Now, this sounds like a lot of caveats, but think of this as equivalent to the change in again, going back to the analogy of mercury, we're talking about the change in volume of mercury with respect to temperature, okay? So important to remember, exposure is an integral quantity that we measure over a period of time, okay? So we're measuring the total number of ionization events that are produced, and that's the exposure. You can also talk about the exposure rate, as in Röntgens per hour or Röntgens per minute at any given point in time. Right. So there's not an SI equivalent unit to exposure, but we do have air kerma, and kerma is kinetic energy released in matter, and this has units of energy per mass, joules per kilogram, or gray. Okay. Now this characterizes the energy released rather than ionizations. So these are 2 separate concepts, but obviously they are closely related. And so you can measure exposure and air kerma. You can estimate them both with those ionization chambers, right? Because if we're operating here, we can get direct measurement of the amount of ionizations per unit time that's occurring. Okay. So this is what these ionization chambers are going to look like. In here, we've got our gas chamber with a voltage applied, and that current is going to be read out here to measure the amount of current running through this. These are operating in that region 2, that current region. Okay. We also have Geiger counters, which is probably more common in the popular imagination. And these operate in region 4, and these are used as measuring as survey meters. Now, because we're operating in that high region, we're getting a full blast of current every time we have any ionization event, which makes them extraordinarily sensitive. And you can calibrate them to measure exposure rate, but standardly, if you don't, if they haven't been recently calibrated for that, you can't use them for that purpose. All right. So, if we're talking about exposure, exposure is an inherent quality to a radiation source, right? It doesn't matter if it's in a vacuum and that radiation is not actually interacting with anything. There's still an exposure related to that specific source of radiation, because exposure is the amount of ionizations that would occur in that unit quantity of air. Okay. Now, if we talk about the energy deposited by that radiation, we're out of talking about exposure, and then we're talking about dose. And when we're talking about dose, it really matters what sort of material we're talking about. Because if you remember in the previous section, the photon interaction in water and sodium iodide are radically different, right? So the probability of interactions is going to be different, which means the energy deposited by that ionizing radiation is going to be different as well. Okay? So dose is measured in rads or grays. And so this is energy per unit mass. And dose can be applied to any kind of radiation, alphas, betas, X-rays, etc. But exposure is only applied to X-ray and gamma radiation. And this is, again, important to remember that this is energy per mass is what we're talking about with dose. All right. So we talked about air kerma, talking about energy released in matter. Right. Now, this is related to a radiation dose, but dose is the energy that's been deposited, whereas kerma is energy released. And so if we're talking about really high energies, energy that's released in tissue could be then deposited in a neighboring mass of tissue. So theoretically something released in the liver could then be deposited in the kidney, for example. Right? So as an example of dose, let's say we've got a patient and we're giving them a radiograph of their whole hand. And this is a cartoon hand where each of the 5 fingers is identical at 20 grams and the palm's 100 grams. And so we acquire a radiograph that uniformly irradiates that subject's whole hand to 1 rad. What would then the dose be to a single finger or to 2 fingers? And what's the dose to the palm here? So let's go back to basics here. What are rads again? It's a measurement of dose, right? And so what are the units there? Dose is energy per mass, right? So we've got, if we irradiate the whole hand, then to 1 rad, that means everywhere in the hand has 1 rad's worth of energy per unit mass. And so it doesn't matter if we're talking about 1 finger or 2 fingers of the palm, everything has 1 rad there. Now, if we switch that around and say, we're going to shield their whole hand and only do a radiograph of their thumb, because only their thumb is broken, okay? And so we have 1 rad to the thumb, then what's the dose to the whole hand going to be? Well, we average that out. So we've got 1 rad's worth of energy in 20 grams. And so the whole hand is in 200 grams. And so in the whole hand, we have 1/10 of that energy average across it for 1 rad. Okay. Main thing to remember here, dose is energy per mass. Oh, so I'm running short on time. So there's a couple quick things I want to cover here. One is that there's a direct relationship between exposure and dose, but that's going to depend on the type of materials, right? So in bone, we've got all this high level of, there's a big conversion factor when converting exposure, Rankine, to rads, dose, in bone. And that's because in that dense bone, we can have that photoelectric effect. So we have secondary electrons produced, which creates more of a dose in the patient. But as we get to those high energies where we don't have to worry about dose or photoelectric effect anymore, this all converges down to the same thing. Okay, I'm going to skip over this a bit to talk about radiation dose equivalent. So, exposure is just number of ionizations produced. Dose is energy per mass. Radiation dose equivalent expands on this more by looking at the type of radiation that's happening and what that biological effect is going to be. And so this is radiation dose equivalent. You take a dose and multiply it by a weighting factor relative to X-rays and gammas. So electrons and betas are similar, but these heavy guys, neutrons, protons, and alphas, do a ton more damage. So, you get 20 times the dose equivalent from an equivalent dose of alphas to an equivalent dose of gammas. Okay. And so if we talk about dose equivalent, we then talk about REMS and sieverts as a extension from rads and gray. Now, the one last item here before I run out of time, is effective dose. And so not only do we, are we talking about weighting by the type of radiation, but we then weight by the susceptibility of a given organ for it. So we get, we sum over the effective dose times the weighting factor for a given organ for all the organs in the body, with how much dose that particular organ got, and that's the effective dose for a whole patient. And so there's tables with these weighting factors, so you can multiply the dose a given organ got by those weighting factors and get the effective dose. And this is what's important for making sure patients are not getting a dangerous amount of radioactivity. Okay, so we're running out. I've run out of time here, so unfortunately I can't quite finish out here. The rest of what I was going to mention is well covered in the Simon Cherry chapters on this, but I will put up all these slides for your perusal as well on the course website. So before we end today, and are there any questions? And I'm seeing in the chat here, sorry I missed this. Yes, the slides will be posted on the course website by Monday of next week. The slides will be up. And once that's set up, I hope to have slides up the day after every lecture.
Cool, thanks.
Sorry, was somebody asking something? I broke up a little bit.
I just said thanks.
Oh, okay, sure. All right, well, no one is rushing to ask questions, so either everything was perfectly clear or you're feeling a bit shy. If you are feeling a bit shy and there is something that you would like answered, again, feel free to email me, and I can do what I can to clarify anything.